Hello Chem 122 students, this is Professor James Ormord and we are going to be talking about coordination compounds today. So without much further ado, let's go ahead and take a look at this PowerPoint that we have ready to go. Alright, so we're taking a look at experiment 27, coordination compounds. We're going to be analyzing a couple different compounds here today. They're both nickel compounds. The main thing that we're doing is we're changing what they are complex to. So here on the right side we have some pictures of the two compounds we're going to be working with today. Nickel 2 chloride hexahydrate. I want to point out that that greenish compound is the hexahydrate, not the anhydrous one. And then the lower one here, that is your hexamine that we're going to be making today in the lab. So short version, we're going to be preparing from the green one, we're going to make the purple compound, and we're going to make solutions of both, and then we're going to analyze the absorption spectra for both compounds today. So take a look. All right, so first things first, in preparing the compound, all we're going to do is we are going to weigh out about 6 grams of the nickel hexahydrate, and we are going to dissolve it in some water, and you'll see later in the lab I did have to heat it up a little bit to get it to dissolve. However, after we make this 10 milliliter solution, I do want to point out that we are going to be taking 10 mils of that to run our samples with, so make sure that you account for that 10% that was removed during your calculation for percent yields. So you should have seen that question also in the pre-lab. So don't forget that minus 10% at the end of the calculation. Or you can do minus 10% of the starting mass, however you want to do it. It'll work either way. Okay, we're going to be working in a fume hood today. We're working with the concentrated ammonium hydroxide. It has a very strong odor. We typically keep it refrigerated to keep the odor kind of down. And then if we were in the lab, I would be yelling at you guys, telling you to only open the bottle underneath the fume hood because the fumes are really obnoxious. So as soon as we mix them together though, as soon as you add the ammonia to the hexahydrate solution, it almost instantly turns purple. And then we're going to place it in an ice bath for about 10 minutes, and then we're going to collect the crystals by a vacuum filtration. And then I do a rinse with acetone to remove trace amounts of water. So you don't want water weight in your final mass. You'll get over 100% yield that way, which is incorrect. Okay, so you guys should remember how to do your percent yield calculation. This is straight from last semester. It's a standard stoichiometry question. I feel that the hardest part on this question is to make sure that you're using the correct molecular weights. So make sure that when you're seeing here that we have the hexahydrate and then we have the hexamine, just make sure that you're using the correct molecular weights, and then you're also additionally, once again, accounting for the loss of the mass from taking the sample for the Spec 20. After you've calculated your theoretical yield, you then take the actual yield divided by theoretical and multiply it by 100%. Okay, in preparing the sample, so after we make the hexamine, we're going to prepare a sample for that by taking about 0.1 grams and dissolving it in some ammonium hydroxide solution. And then we cover it with parafilm, which is, it's almost like I call it like lab saran wrap. It's just a plastic material we can use to cover beakers and whatnot, and it helps keep the odor down in today's experiment because we actually work on the open bench when doing the analysis with the spectrometer. All right, I will go over this in detail during the procedure itself, but we are going to be going from a range of wavelengths here that we're going to be analyzing in 15 nanometer increments. So starting at 450, going up to 750, 15 nanometers at a time. Make sure that whenever you change the wavelength on the spectrometer, you must do a new blank. So the way we analyze the blank is we put it into the spectrometer, and then we adjust the knob to say, such that the transmittance reads 100 and that the absorbance reads 0. And remember, every single time the wavelength changes, you must adjust that knob a little bit again, to reblanking essentially, because every single time you change the wavelength, the absorbance will shift by quite a bit. So your data will be notably terrible if you do not do this step. And it'll be really obvious to anybody who's ever worked with Spec 20 before, that it'll be really obvious in the data that you did not adjust your knobs as you were going along. All right, let's go ahead and pretend that we have the data. And I'm going to go ahead and show you guys how to work with the data here. really quickly. I recommend that we use Excel for this. You can do this by hand, and I would actually communicate with your lab instructor which one they want, whether they want you to do this by hand or by Excel. But for my students, I would have them use Excel. All right, for this next part, I want to show you how to use Excel to plot your data. Remember that you want to make sure that your lab instructor wants it this way, otherwise do it by hand. So I'm using the free version here. Let's go ahead and take a look. So here I made some pretend data. So we have our wavelength in nanometer. We're going to be starting at 450 and going in 15 nanometer increments. So you could do that manually, but we're going to use the power of technology to do it for us. All right, so let's go ahead and say equals. So I'm using a function here, something equals to that cell plus 15, and then it should calculate it for us. And then Excel is really good at doing iterative calculations. So all they have to do here is grab this little box in the bottom corner here and then drag down like so, and then it autofills all the different wavelengths here. Okay, and then I made some pretend data here. Just remember, this is pretend data. Your actual data will look a little bit different. And I'm actually going to tweak this. Let's go with this. Anyway, so the way we do this here is you want to go ahead and highlight all the data. Remember, you want it in the format with the x-axis data is on the left. That's typically how Excel is going to recognize it. And then here we go to Insert, and then Scatter Plot, and then you should see the type of plot we want in here. So this one right here is showing 2 overlaying, and we want to go with that one. And here is the data graphed out. We're going to edit this a little bit. So here I'm going to go ahead and right click and then go to Format, and then here we're going to get a bunch of options. If you're in the paid version of Excel, these options are typically in the top bar there. Anyway, I'm going to change the title here. So the chart title is going to be absorbance nickel compounds. And then it should change it up there up top. Yep, it did. We'll do the legend here. We can leave the legend alone for a second there. The horizontal axis, we're going to have to modify this. I don't like the range here, so our range is actually 450 to 750. So I'm going to have that to be my bounds. So 450 to 750. And notice how it's kind of zooming in on the data. Whenever you make a graph, you want to utilize all the graph space if you can. And then here we can pick out what the lambda maxes are, but I'll show you guys here in a moment how to get it from the data. And then series 1, it looks like, actually, series 2 I'm going to change. So we'll say that's the green compound. You can make that green if you'd like. Be for real. All right, made all those green. And then, are you for real? They waited for me to start recording. This one's going to be purple. This is the purple compound, and it should make it purple on the graph itself. You don't have to do it, but I like to do the graph that way, where the color of the line matches the actual color of the compound, because yeah, that's how I am. Here we should also label the axes here. Let's take a look at the options again. So horizontal axis. Typically there's a way to label these, maybe not in the free version. You could do it by hand, but I know in the paid version you can actually label these axes with text. I am not seeing that option. Sorry. This is sufficient enough to me, though, to be honest. All right, so after you have this, you can just go ahead and pick out in the data where the maximums are, and then what wavelength that corresponds to. You can actually use Excel for this as well. So I'm going to go ahead and make new entries down here below the data. So let's say absorbance maximum. So ABS max is for absorbance maximum. And then we're going to say lambda max, which is the value that you actually want to get for each of these compounds. So what I'm going to do here is I'm going to make a command that'll actually search out the largest value here. So it's equal max, open parenthesis, and then you want to select that entire data set, and then close parenthesis, enter, and there we go. So if you're unsure what you've typed in, if you click on this and actually look towards the top here, it's showing you what the command is right here. And then all they need to do now is just find where that value is. It looks like it corresponds to 615. So 615, I'm doing that manually. I'm sure there's ways to have Excel call to that too, but I'm not going to bother here. Equal max, and then this set of data, close parenthesis, there we go, it's 0.72, it looks like that occurred at 600. Once again, for like the 50th time, this is not the real data. So you want to do this with the real data. All right, so that's pretty much all we have to do with the data for this particular experiment. Remember, we also do need to calculate percent yield, but I meant the actual spectra data. This is what we're doing here. All right, so let's go take a look at the experiment now. Okay, I want to talk in a little bit more detail about the chemistry that's going on here. So we are essentially starting with the nickel hexahydrate. So the way you want to write these is you want to make sure that the ligands, things that are grabbing the metal, go with the metal, like that. And then you want to put the brackets around it to let the reader know that this is the complex ion. And then your anion here is 2 chloride ions. We're going to be treating this with 6 moles of NH3. This is the mole equivalence here. And what happens here is we actually go into this in a lot of detail in organic chemistry. But it turns out that the lone pairs essentially have stronger affinity to grab things essentially than the lone pairs in oxygen do. So the short version of that basically means that the nitrogen atom here is a stronger ligand than oxygen is. And being that it's a stronger ligand, it'll displace the water. So we're going to get basically 6 of the ammonias with the nickel. And then the 2 here don't change. And then what came out here. So remember we have a thing called the coordination number, and the coordination number is essentially telling you how many ligands sites does the particular metal have. So for this one here, being that it has 6 ligands here, then this has a coordination number of 6. And recall from earlier, I mentioned that this one is green and this one is purple. So it's really clear if the reaction is happening or not. The next thing I want to talk a little bit about is how to draw these. They can be challenging. Because we have 6 groups coming off the central atom, it works out that these are going to be an octahedral. And the way I like to think of the shape of an octahedral is that you have basically a pyramid with a square bottom. You could think the Luxor Casino is basically a square pyramid. But imagine that the pyramid goes up and down. So we have the square in the middle. Let me draw out kind of what I'm talking about here, what the shape is. And then I'll actually draw the actual compounds. So you can imagine that's a square. And then they all come to a point with the pyramid. So there's your square pyramid. And then this also goes downward as well. And then we have the parts behind that we can't see. Like that. So it's an octahedral shape. You can also think about it if you play board games. This is an 8-sided die. So the way we draw this, there's a couple different ways we can draw this, but I like to emphasize that we have the square in the middle. And I think if you do that, the rest of it's fairly simple to draw. So I'm going to show you 2 different ways to draw this. One of them I think is the easier way. So I'm just going to go ahead and draw this one. And all you would have to do is just change out for the waters for the other one. So there's our nickel. And in order for this to be a square shape along the middle here, the way you could draw this is have one of these coming towards you like that, and the other one going away like this. So that's actually making a square shape, but we're kind of seeing it essentially like if we turned this is essentially the way we're looking at it. And then we have the other ones that are straight up and straight down. And then you go ahead and add your ligands on. So this will be NH3. And then I'm going to have them where the nitrogen is pointing towards the nickel, because that's where they actually chelate from. So I'm going to have to flip the orientation on this side to show it like that, just to emphasize that the bond is between nitrogen and nickel. You don't want to be ambiguous here where the bonds are. We will get a lot more particular about that next semester. Another thing that students will often forget here is that these are complex ions. So remember, for ions, we have to put the brackets around them. Oop, kind of a messed up bracket there. And then we get our charge on the outside, like so. Okay, another way to draw this, I think is the more challenging way, is that if you have these all out of the plane of the paper. So nickel, and then just like before, I like to focus on the square. So in order to draw this square, I'm going to have two of them coming towards us, and then two going away from us. That is essentially the view that I drew up here originally, but I feel that it's harder to draw when you're doing the dash wedge thing. And just for the sake of completion here, let's go ahead and make this one the water one. So the way I want to draw this here is I want to make sure that the connectivity is shown to be between the oxygen and the nickel. So oops, these are H's, not N's. Sorry about that. I was thinking the last setup here. And then H2O, H2O. Notice here how I'm always showing the bond oxygen, nitrogen. Sorry, oxygen, nickel, and the same nickel, nitrogen. And then you put your brackets. And then don't forget the 2+, like so. Another thing you're going to have to talk about with your lecture, as well as in this lab report, is the type of ligands we have here. So these particular ligands are referred to as being monodentate, meaning that they can only grab one time. And as you should have learned from your lecture, there are two in particular that you should have learned. I believe the first one is ethylene diamine, which is dibentate, meaning it has two. And then EDTA, ethylene diamine tetraacetate, is a really common one. And let me go ahead and draw these out and show you how these grab things. So your EN for short typically, this is ethylene diamine. And drawing the structure here, we have two nitrogen groups like that. You probably haven't learned this shorthand here. This is organic chemistry shorthand for carbon structures. But essentially what this is here is at the corners here, that is each of these is a CH2 group. So it's CH2, CH2, we just shorthand it with the squiggly lines. The other one is actually fairly similar. The big difference here, instead of the H's coming off, we have more complex carbon groups. So this next one here is EDTA, ethylene diamine tetraacetate. And as you guys will see next semester in organic chemistry, the naming on organic compounds is very deliberate on the structure. So the main portion in the middle is the same. And then we have one carbon spacer. And then we basically have the fingers here, I like to think of them as. These are going to be what's doing the grabbing. Are these negative pieces that I'm drawing here. And you could show different charge versions of EDTA. I'm showing the one that would have a -4 charge, but there are different variations of this as well. Okay, so taking a look at both of these particular ligands here, these can each grab more than one. It works out where this is dibentate, and then this can grab two, and then it works out for this one. This is a great chelating agent. Remember, chelation means handed, so you can think of these as being basically fingers that are going to grab onto a metal. They can actually use this type of chemistry to help with toxicity of metal consumption. So if you were to swallow a bunch of lead, they might treat you with something like EDTA to chelate to the heavy metal. This particular compound is commonly used for treating heavy metal poisoning. All right, everybody, I think we're ready to get started on the experiment today. I'm going to go ahead and start off first by weighing out. Actually, I'm going to start off by first putting my goggles on. I already have my gloves on. But we're going to start off by weighing the nickel 2 chloride hexahydrate. So make sure that you remember that it's the hydrate, and you include the mass of the waters in your molecular weight. And here the bottle has a formula weight of Go ahead and use that number there. I'm seeing 237.71. Okay, I'm going to go ahead and use a little weigh boat. I'm going to go ahead and put it on the scale and tare it, and then when I get a weight, I'll bring the camera over. We can get a nice view of it. So, tare. Remember, taring, you're zeroing out the scale. There it goes. All right. And like I said, I need 6 grams. I wanted to point this out here. This is a like lime green solid here. Pretty cool looking. It's going to take quite a bit of this, so I'm just going to go ahead and pour it in. See what you got. I went a little bit over. It is okay. Just make sure that you get this exact mass. So 6.2467. Okay, now let's go ahead and take this over to the fume hood and dissolve it in some water. All right, for the next part, I'm going to go ahead and take my solid and 10 milliliters of water, which I went ahead and measured out in a graduated cylinder. And then I'm going to go ahead and pour this into a test tube. Back up a little bit. I'm going to pour some of this in here. Remember to be careful. And then I'm going to go ahead and transfer my solid into this. And hopefully I don't make a huge mess. Get no color change when it's going into water, which is normal. We weren't expecting a color change here. Like I said earlier, it's not really dissolving very well. In the case where it doesn't dissolve all the way, you can centrifuge it, but you want to make sure that your solution is not cloudy when you're doing the spectroscopy part later. Okay, you can see it's not fully dissolving. I'm going to go ahead and heat it up now in the hot water bath that I have started. And let that sit for a few minutes. Okay, it looks like I got it all to go in solution. And remember, in the case where if it's cloudy, you want to centrifuge first. You don't want cloudy solutions in the Spec 20. It won't work very well. For the next part, I'm going to go ahead and measure out 12 milliliters of the concentrated ammonium hydroxide. Remember, if you're ever working with this stuff, you always want to use your fume hood. Very strong vapors. Be thankful we don't have smell-o-vision yet. All right, we got about 12 milliliters. Definitely want to make sure you reclose this lid. I'm going to transfer the liquid from earlier to a larger test tube, and I'm going to put it in the ice bath. And then I'm going to have it on the ice. I want you guys to be able to see it though, so let's put it like that. And then we're going to slowly add some of the ammonia. Should see a color change almost right away. Yep. I don't want to add the rest yet. I want to kind of show you this up close. See the purple color forming there on top? That is your nickel hexamine. And then after I get all of this in here, I'll give it a good shake. Make sure it's all mixed up. Spilled a little bit there. Okay. The ammonia should be in far excess here. Still see a little bit of the green in the bottom. Okay, this reaction mixture has been sitting in the ice bath now for about 15 minutes. I left it in the fume hood here. See a nice purple color there. Take a nice little look at it here. Okay, we're going to use a vacuum filtration here. We're going to use a tearaway here. When working with these, I recommend that you take the cup portion and then throw a piece of filter paper in there, and then your tape, and then weigh the whole thing. So that mass there is from the scale. It's the weight of the cup with the paper in it. And then we're going to get the mass by difference at the end. When working with one of these, I recommend that when you wet your paper here, that you wet this with whatever solvent you use. So last time we used water to wet these with. Today our solvent is not actually just water. Remember, we have ammonia in here too, so I'm going to go ahead and use ammonia to wet this down with. Nice, pretty purple color. Can you see it okay? There we go. So if you're doing a rinse step, I recommend you turn the vacuum off first and then add a little bit of your liquid to there and then turn the vacuum back on. We're just giving it a nice acetone rinse to help drive the water, any water off. And then we let it sit here for a few minutes to dry, and then we'll get a mass to calculate a percent yield with. Okay, we're ready to go ahead and get a weight on this, but first I wanted to show it to you. Got a nice fine powder there. Nice purple, what we're expecting. Already zeroed out the scale. Let's go ahead and put it on here. And you will get the mass by difference and calculate a percent yield. All right, let's go ahead and take it back to the fume hood. Okay, for this next part here, I'm going to go ahead and prepare a solution. We're going to take, it says in the procedure to take about 0.1 gram. Honestly, it's about a scoop, a little teeny scoop. And then I'm going to add some ammonia to it. Pipette from earlier. I'm not worried about being exact here. Gonna get about 10 milliliter. One more scoop probably is enough. Also, looks like I need more. I'm actually gonna put more solid to make it a little bit darker. This won't have really good absorbance then. This next part is actually more qualitative than quantitative, so that's why I'm not worrying about the exact amounts. Got a little bit of pressure from that, from the ammonia. That's pretty high vapor pressure. And then after we get this ready, we're going to cover with parafilm to keep the odor down in the actual lab. See that?
Yeah.
See any more? Yeah, make it a little darker. It's usually pretty dark. I guess I could have weighed out the 0.1 gram. All right, we'll get this all mixed up, and then I'll get my blanks ready, and then we'll move over to the spectrometer. All right, we're now ready to go ahead and start analyzing on the Spec 20. It's right here behind me. So a few comments here first is one, we have to start this a little bit in advance. It's been sitting here for about an hour, but honestly, you need just about 20 minutes for it to warm up. Another thing too is you want to be aware of is the filter switch right here. So there is a filter switch there for which wavelength range that you're in. So for example, if you're at 450, which is what I'm at right here, I should be towards the left. And then as soon as you go over 600, don't forget you have to flip over, otherwise any data past 600 is poor. Okay, and here I have a blank. It's just water. Technically the blank should be everything except for your analyte. And I guess technically we should have a blank for this one. That's ammonia, not just water. But we found over the years that it makes little to no difference if we use water for our blank for both of these. So the way we're going to do this is I'm going to, at every wavelength, blank for water, and then measure the hydrate, and then measure the hexamine in that order. So blank, hydrate, then hexamine. Okay, let's get started. Okay, start off with the blank. You want transmittance to be 100 and absorbance should be 0. And you barely have to turn them to make a move. Very sensitive. Oh, good thing I have the parafilm. All right. Then we toggle to absorbance. Should be 0, and then now we can measure. So take the blank out. This one. And I'm going to record these values along with you. So for the first one, for the hydrate, we have 0.206. I need a new pen as well. And then for the amine, we have 0.023. Okay, now the fun part. So we're gonna change the wavelength. That's the knob here on the top. And don't worry about what that's doing right now. It doesn't matter. So we should have it 165. I'm barely turning this. I want to skip that number. There we go. All right. And then you have to re-zero with the blank. So back to transmittance. See how different that is just by changing the wavelength? So yes, it does matter. You have to do this. think they should have to go through this torture too. Us having to wait through it. No time lapse. Oh, come on.
If it starts doing something weird, you might pop the test tube out and make sure it's square in there. Because remember how it's supposed to be cubic.
Yeah.
Sometimes it gives off and it smells. You get custom noise from it too.
Yep. All right. Good enough. Let's go ahead and get some measurements. Always make sure to close the lid. Otherwise, and then 0.132 for the hydrate. Zero point 0.018. All right. Rinse and repeat. Okay, we are now at 600 nanometers. Don't forget that you have to flip the filter switch here, otherwise your data is bad at this point on. So flip, and then you don't change anything else. Just continue as normal, but you have to make sure you flip this at 600. All right. Have them do a first derivative plot too to get the data.
What?
The first derivative plot. All right.